Okay, we're going to look at 10.5 and 10.6 today. What this whole section has been about, the whole section has been about similar figures. And what we know about similar figures is that their angles are the same. And then their sides are proportional. And so that's how we can tell if two angles in a triangle are the same, then the third angle is going to be the same. And so as long as all the angles are the same, it will be proportional in a triangle. We cannot say that about a rectangle, because you can have a rectangle and a square. They are not proportional, but they all have the same amount of right angles. Okay, so in a triangle, if two angles are the same, then the triangles are similar. So that's one thing we know. Okay, so these are some things we know about similar figures that we've talked about so far. Okay. Working a lot with proportions and ratios here. That's what this whole thing is about, is going back and looking at how do I work with proportions and ratios. It's scale modeling, stuff we do all the time, like the violin and a cello and those things. They are made in a certain ratio compared to the violin. That is how they construct them. Okay, they make it bigger. It's actually the same instrument, just made bigger. And so it has a different sound because it's made bigger. So in 10.5, we're just adding another similar one. I think I mentioned it to you a long time ago, almost 2 weeks ago. It is if you have two similar right triangles. Is it right or is it just regular triangles? Just a minute, I might have to see something. Maybe just. Oh no, it's any triangle. Doesn't have to. If you have two similar triangles, then their altitudes have the same proportion as their sides. Okay, so if we have a triangle that looks kind of like this, that was not meant to be identical, but okay. So we know that they're similar triangles. Okay, so that means that X, Y, and Z, A, B, and C, X over A is the same as Y over B, which is the same as Z over C. Okay, if they're proportional, that's what we know, that the sides are in the same ratio. So the X corresponds to the A, the Y corresponds to the B, the Z corresponds to the C, so these are all equal. That proportion is equal. Okay. If we take their altitudes, which is really what we saw in the violin program thing, that when we find the altitudes, the heights, because when we drew that triangle out, we found that the heights are also in the same ratio. So I'm going to call this height 1 and height 2. So height 1 will equal over height 2 will be in that same ratio. Okay, so This is the new thing that we're looking at right here, is it's going to be in that same ratio. Okay? Which kind of makes sense because if we made the triangle bigger, obviously its height is going to be made bigger also in that same amount. Okay? So that's basically what we're looking at in 10.5. So they're just having you work with that kind of thing. They're going to talk a lot about dilations. Dilations is, again, you can make dilations when you're looking at triangles and stuff. You can always have a point of reference. And if you do something like this, if you put it here and here, those will be in the same ratio, okay? If you take, these will be similar triangles because this one is the same, and these, as long as they're parallel, this angle will be the same as this, and this angle will be the same as this because our lines are parallel, okay? And so that's where we can go through this, and we can find out that you can put a point out anywhere from two similar figures, and you can make a dilation that goes out with them with triangles, okay? They do that a lot with drawings that are perspective. They will put that reference point out there so they can draw them exact. So we know that it's exactly the same size. Okay, without measuring, you can draw your triangle out and then draw your things the same height, and you know it's exactly in the proportion that you want it. Okay. So that's basically the same idea there. Questions on that? Anything to do with that? Okay, that's really 10.5. Really simple. Okay. 10.6 goes into a little bit more, but you have worked with it before. You did some problems in a previous section to see what they were, and so you've actually seen this prior. Okay, so 10.6 is looking at in similar figures, what's the difference in their areas and their perimeters and, perimeters and areas, okay? So if we have, we're going to look at how perimeters, what are they, and how are their areas, okay, related. So if we have two similar, let's just do a triangle. And this triangle, okay. We'll use this triangle to see about perimeters. We're also going to use it to see how the areas are related, okay. These are right triangles, by the way. What is my ratio between these two? Between the two similar triangles? What's the ratio of dilation? How much did I make it bigger? 2. Okay, so this, my dilation is equal to 2 because I doubled each of the sides, okay? If I put the ratios of each side together, we could do it as 6/3 equals 10/5, which equals 8/4, which equals 2. You see that my ratio of dilation, so I'm doing the bigger to the smaller, it is 2. Okay, so we dilated it by doubling it. Okay, so let's look at the perimeters. How do I get a perimeter? What does perimeter mean? Perimeter. Meter means? What does meter mean?
A little less than a yard.
It's a little less than your, it's a measurement. Okay, meter means measure. A periscope on a, what does a periscope do on a submarine? Does anybody know?
So,
Periscope on a submarine. Does anybody know what that does?
yeah, I know it does.
What does it do?
It lets you see.
See, where?
Around.
All the way around. Yes, a periscope. So peri means around, all around, 360 degrees, okay? And meter means measure. So perimeter means to measure all the way around the outside of the figure. Okay, that's how perimeter is actually, it comes from base roots that mean measure all the way around. Okay, a lot of words are like that. English and math have that in common, that if you know the base definition of peri and where it's used other places, you can use that to help you figure out what these mean. Meter means measure, okay? So if I measure the whole distance around here, what is it? Lucas, what is the measurement of the small triangle all the way around?
Sorry, I'm really tired. 12.
12, okay? So the measure of this, the perimeter of the small is 12, okay? What's the perimeter of the large, Harrison?
It is 24.
24. Okay, so I did my ratios up here of large to small, large to small, large to small, and that was equal to 2. So I'm doing the perimeter, large to small. What is its ratio? It is also 2. The ratios of the perimeters will always be the same as the ratios of your dilation. Okay, so your ratios will always be the same. So perimeter stays, because it's not squared or anything, perimeter stays as the same dilution. If the size of the perimeter of one will be twice the perimeter of the other if the dilation is 2. Okay, so they stay the same ratio. That's basically one of the things it tells you, okay? That works on all polygons that are similar. And that works not just on triangles, but that works on all polygons that are similar, okay? Areas, we're gonna use these same 2 triangles, okay? So we have 3, 4, 5. Oops. Might not be drawn to scale. How do I find the area of a triangle? Like, how do I find the area of a triangle?
Multiply both sides and divide by 2. Or
Both sides. What would be both sides in this case?
I'm at the base and height.
Okay, the base and the height. Okay, so in this case, the base and height are the legs of the triangle because it's a right triangle. Okay, so our formula for area is equal to the base times the height divided in 2. Because really, if you think about it, a triangle is just half of a rectangle. And to find the area of a rectangle, we've just multiplied the length times the width, or the base times the height. Okay? What is area finding? What are we actually looking for? Aaron, what am I actually trying to find with area?
How much is inside of it?
How much is inside of it? How many little squares fit inside that are whatever our measurement unit is? Okay, so if it's an inch by an inch, how many little squares that are an inch by an inch fit inside? This we don't have any units, so we just call it square units. Okay, so what is the area of the first one? Luke, what's the area of the first one? The area of the first one is 6. So the small triangle, the area is 6. Okay, we're going to do the ratio that way. Okay. Lene, what is the area of the second triangle?
18, no, 16.
Is it 16? 6 times 8.
Oh, is it 12? 24.
It is
That
24.
was weird. My math is somewhere
So the
else.
large area is 24, which if I reduce that down is 4. How is it related to the first ratio? Our first ratio is 2. How is 4, the area, related to that? Ratio. Okay, the ratio of the figure is 2. How is 4 related to 2? Any way you can tell me how it's related?
It's double.
It's double. So we could say it's 2 times 2, right? How else can I write 2 times 2? How do I write repeated multiplication? 2 what? 2. Elijah, what is 2 times 2? It's 2 to the power of 2. It's 2 squared. 2 squared equals 4. The area is always the square of the ratio. So the area is the square, the ratio of the areas, I should say, the ratio of the areas the square of the ratio of the figure. And that kind of makes sense if you think about it. We're trying to find out how many little squares are inside. Okay, when we make the size bigger, we're going to actually have to square that. So that's why the ratio is always squared. So the areas of similar figures are always the square of the ratio of the original figures. Okay? So that's something that you can use when you're going through it. So that's something that you're going to look at in this section. So today, we get to start using our whiteboards again. So we're going to take some time and I'm going to give you some problems to go do at the whiteboards. Because I love using whiteboards. I think it's fun. Okay, I'm going to turn this off.